Hello there, and welcome. I am so glad you have found your way to this quiet corner of the cosmos. Perhaps the day was long, filled with noise and haste. Or perhaps you are simply one of those souls who finds comfort not in counting the sheep, but in weighing the silence between the stars. Either way, this journey is for you. There is nothing left to do but to let go. Allow your mind to soften, your breath to deepen, and your body to feel light, as if gravity itself has decided to loosen its hold, just for a little while. Tonight, we are not seeking answers. The universe is not a book to be finished, but a poem to be felt. We are here to listen, to drift through the grand, silent questions that have echoed in the minds of thinkers for 100 years. These are not problems of mathematics, but mysteries of existence itself. They are the quiet hum beneath the beautiful music of the cosmos, the deep shadows that give the starlight its meaning. We will not solve them. We will simply be with them. We will let their immense and gentle weight guide us into a deeper state of rest. So close your eyes, let the world outside fade away. Tonight we travel not to destinations, but into the heart of the great unknown, one soft question at a time. Across the vast, spinning tapestries of the night, galaxies turn in a slow, luminous dance. From our distant perch, we see them as perfect islands of light, held together in a graceful, spiraling embrace. We see the dust lanes, dark and cool, tracing paths between the arms. We see the brilliant blue of newborn stars and the soft golden glow of ancient suns at the core. It all appears so orderly, so serene. A celestial city built on foundations of gravity, following rules we have known for centuries. We expect the stars on the outermost edges, the lonely pioneers at the frontier of the galactic disk, to move slowly, leisurely, like planets far from their parent sun. Gravity's grip, we believe, should grow weaker with distance. The farther a star wanders from the dense, bright heart of its home, the more slowly it should orbit, its long path a testament to the fading influence of the center. This is the logic of things thrown, of planets in their orbits, of the universe as a grand, predictable clockwork. It is a comforting thought, a universe that obeys the simple, elegant rules we have discovered. And yet, it is not what we see. When we listen closely with instruments that can measure the faint, ancient light from those distant edges, we find something unsettling, something beautiful and strange. The stars at the galaxy's rim are not slowing down. They are racing along their paths with an impossible velocity, a speed that should have flung them loose from their gravitational tethers billions of years ago. They are moving as if held in place by a force we cannot perceive, a grip far stronger than all the visible stars and shimmering gas clouds combined. The galaxy does not turn like a solar system. It turns like a solid wheel, its edges keeping pace with regions much closer to the heart. It is a motion that defies all of our calculations, all of our expectations of how matter should behave. It is as if the entire magnificent structure, every star, every planet, every cloud of dust, is embedded within enormous, invisible scaffolding, a silent, unseen architecture that holds the luminous matter in place, preventing the beautiful, spinning city of light from flying apart in the cosmic dark. This ghostly structure is everywhere, surrounding the disk, filling the halo, extending far beyond the faintest, most distant star. It is the vast, quiet majority of our galaxy, and yet it has never been seen. It is a ghost in the grand machine, a silent partner in the cosmic dance, whose presence is known only by the impossible grace of the stars it holds. We have searched for this hidden substance, this missing mass, for decades. We have built detectors deep underground, shielded from the noise of the cosmos, hoping to catch the whisper of a single ghostly particle as it passes through the Earth. We have pointed our most powerful telescopes at the empty spaces between the stars, searching for a flicker of light, a faint distortion, any sign at all of its presence. But the search has only deepened the silence. This dark matter, as we have come to call it, does not shine. It does not reflect light, nor cast a shadow in the conventional sense. It does not seem to feel the touch of electromagnetism, the force that governs nearly everything we know and see. Light passes through it as if it were not there. Our own bodies, the very planet beneath us, are thought to be drifting through a constant gentle rain of these particles. Yet we feel nothing. They slip through the spaces between our atoms, through solid rock and dense metal, as effortlessly as a dream passes through the mind of a sleeper. It is a profound and humbling realization that everything we have ever seen, every star that has ever been named, every galaxy that has ever been photographed, makes up only a tiny fraction of the universe's true mass. We are living on a small, luminous island in the middle of a vast, invisible ocean. The substance that governs the shape of our galaxy, that dictates its destiny, that laid the very foundations upon which stars and planets could form, is utterly alien to us. We do not know what it is made of. We do not know its nature. We only know that without it, the universe as we see it would not exist. It is the quiet, invisible framework of reality itself, a substance defined not by what it is, but by what it is not. It is the universe's greatest secret, hiding in plain sight in the elegant, impossible motion of a distant star. It is the gentle, gravitational hum beneath the silence, the unseen skeleton upon which all the beauty of the cosmos is built. And perhaps its mystery is not a problem to be solved, but a quiet reminder. A reminder that the truest, most fundamental aspects of existence may forever lie just beyond the reach of our light. They are not to be seen, but to be felt in the steady, silent turning of the stars. Long ago, we looked out into the cosmos and expected to see a universe that was slowing down. The great explosion of its birth, the Big Bang, had flung everything outward. But the mutual gravity of all the galaxies, all the stars, all the matter, should have been acting as a gentle brake. Like a ball thrown into the air, we thought. The universe's expansion must be decelerating. Perhaps one day it would come to a halt and begin the long, slow journey of collapse, returning to the single point from which it came. Or perhaps it would slow forever, drifting into a cold, quiet equilibrium. For billions of years, this was our story of the cosmos, a story of inertia and gravity, a narrative of a universe gradually losing the energy of its explosive creation. It was a story that made sense. It felt complete. It was a future we could comprehend, written in the laws of physics we knew so well. It was a universe settling into its old age, its youthful fire fading into a long, predictable twilight. But the universe, it seems, had a different story to tell. When we learned to measure the distance to the farthest galaxies with incredible precision, we found something that shook the very foundations of our understanding. The universe is not slowing down. It is accelerating. The expansion is getting faster and faster with every passing moment. Galaxies in the distant reaches of space are not just moving away from us. They are rushing away at ever increasing speeds. It is not a violent push, but a gentle, persistent, and inexorable force woven into the very fabric of space-time itself. It is as if space is not an empty stage upon which the cosmic drama unfolds, but an active participant, a living thing that is slowly, quietly breathing outward. This cosmic acceleration implies a future far stranger than we had ever imagined, a future of profound and growing solitude. It means that, billions of years from now, all other galaxies will have rushed away from us so fast that their light will no longer be able to reach us. They will disappear beyond a cosmic horizon, one by one, leaving our own Milky Way alone in an endless, silent, and observable void. The night sky of our distant descendants will be dark and empty, the rich tapestry of galaxies we see today having faded into an unreachable memory. The universe is not coming together, it is drifting apart on a gentle, accelerating tide of pure, empty space. The source of this strange, repulsive force is perhaps the deepest mystery in all of science. We have given it a name, dark energy, but a name is not an explanation. It is merely a placeholder for our ignorance. Unlike gravity, which arises from matter and pulls things together, this force seems to arise from nothing at all. It appears to be a property of the vacuum itself, an intrinsic energy contained within empty space. The more space there is, the more of this energy there is, and so the faster space expands. It is a force that grows as the universe grows, a quiet, self-perpetuating engine of expansion. It does not dilute or fade away. It is constant, eternal, and woven into the very essence of reality. Think of it not as a force in the traditional sense, but as the quiet, relentless will of space to become more of itself. This idea is profoundly unsettling. It means that the emptiness between the stars is not truly empty. It is a simmering reservoir of energy, a hidden wellspring that is driving the cosmos toward its lonely fate. All the matter and energy we can see, all the stars and galaxies, are just a minor component in a universe dominated by this invisible, mysterious influence. Dark energy makes up nearly 70% of everything that exists. We live in a cosmos whose destiny is not shaped by the brilliant light of suns or the pull of galactic masses, but by the quiet, persistent hum of the void. And so, we are left to wonder, what is this energy that springs from nothing? Is it a fundamental property of our universe, or a temporary phase? Is it the echo of some deeper physics we do not yet comprehend? The accelerating cosmos does not offer us answers. It only offers a deeper, more profound sense of awe. It paints a picture of a universe that is not static or mechanical, but alive with a strange, dark vitality. A universe that is not just expanding into space, but one where space itself is the engine of its own endless, quiet, and solitary becoming. Our entire cosmos, every star you have ever seen, every world that has ever been imagined, was once contained in a space smaller than a single grain of sand. This is the story of our beginning. It was not an explosion in the way we might picture a star bursting in the darkness. There was no darkness for it to burst into. There was no space. There was no time. There was only this point, this singularity, a state of infinite density and heat, holding within it the promise of everything that would ever be. It was not a beginning in time, but the beginning of time, the first tick of the cosmic clock. Before this moment, the word before had no meaning. There was no past, no future, only an eternal dimensionless now. From this single silent point, space itself began to unfurl. It did not expand into a void. The void was created as it grew. In the first fleeting fractions of a second, the universe swelled from the infinitesimal to the immense, an event so rapid and so vast it is almost beyond comprehension. This was the birth of distance, of direction, of the very stage upon which reality would be built. The fundamental forces that govern everything, gravity, electromagnetism, the strong and weak nuclear forces, were born in this initial fiery breath, separating from a single, unified essence like colors, separating from pure white light. The universe was a featureless, searingly hot soup of pure energy, a brilliant, opaque fog of light so dense that nothing could travel through it. It was a perfect, seamless, and unimaginably bright furnace, where the laws of physics were still being written. As space continued to expand, it began to cool, and in this cooling, a great transformation occurred. The raw energy began to congeal, to crystallize into the first, elementary particles, the fundamental building blocks of matter. Quarks and electrons and neutrinos flickered into existence, born from the fading heat of creation. For thousands of years, the universe remained a glowing, impenetrable plasma, a swirling chaos of light and charged particles, locked in a furious dance. No stars could form, no galaxies could gather, no atoms could yet hold together. It was a universe of pure potential, a brilliant but formless sea of becoming. Then slowly, patiently, after 380,000 years of expansion, the cosmos cooled enough for the first atoms to form. Electrons were captured by protons, and the universe for the first time became transparent. Light was set free. The brilliant fog cleared, and the darkness of space, as we know it, was born. This first ancient light released in that moment of clearing still travels across the cosmos today, stretched and cooled by billions of years of travel, a faint ghostly hum of microwaves in every direction we look. It is the echo of our birth. From that moment on, gravity, the quietest and most patient of all the forces, began its slow and monumental work. It gathered the newly formed clouds of hydrogen and helium, pulling them gently into vast, spinning structures. It coaxed them into the first stars, brilliant, massive, and short-lived, which ignited the darkness with their nuclear fire. And in the hearts of those first stars and in their explosive deaths, the heavier elements were forged, the carbon, the oxygen, the iron, the very substance of which planets and eventually life would be made. Every atom in your body, the iron in your blood, the calcium in your bones, was created in the heart of a long-dead star, a descendant of that first singular moment. We are, in the most literal sense, stardust. We are the children of that initial, silent unfolding. The entire, vast, and intricate story of the cosmos, with its 13 billion years of history, was contained within that first, quiet, and impossibly small seed. It is the ultimate origin story, a tale of a universe born not from a sound, but from a silence that contained all possible sounds. The human mind, in its quietest moments, cannot help but ask the question, what came before? If the universe began with a single, infinitely dense point, what was the state of things a moment prior to its unfolding? We try to imagine it, this state before time, but our language and our logic falter. The very words we use are tied to a reality that did not yet exist. The word before implies a timeline, a past to which we can refer. But if time itself was born in that moment, the question becomes a paradox, like asking what lies north of the North Pole. Our science, our mathematics, our deepest theories of physics all lead us to this same silent wall. At the singularity, our equations break down into infinities, and the known laws of nature cease to apply. We stand at the very edge of what can be known, and are left only with the vast, quiet expanse of speculation. Perhaps there was nothing, not the empty space we think of as a vacuum, which is still a place and is simmering with quantum energy, but a true absolute nothingness. The absence of space, the absence of time, the absence of matter, energy, and even the laws that govern them. It is a state that is impossible for us to visualize, for our minds are built to perceive existence, not its utter negation. It would be a silence so profound that it would not even have the potential for sound, a darkness so complete that the concept of light would be meaningless. If this is the case, then our universe is the ultimate miracle, a spontaneous fluctuation from non-being into being, an impossible something born from an absolute nothing for no reason at all. It is a thought both terrifying and beautiful, that the entire magnificent cosmos might be nothing more than a temporary accidental dream in an eternal shoreless ocean of non-existence. Or perhaps our universe is not the first. Perhaps it is just one chapter in an endless cyclical story. This idea, known as the Great Bounce, imagines a universe that has existed forever, contracting and expanding in a great cosmic rhythm. In this view, what we call the Big Bang was not a beginning from nothing, but the moment when a previous collapsing universe reached a point of maximum density and rebounded, beginning a new cycle of expansion. Our cosmos then would be the child of a dead parent universe, its matter and energy forged in a previous existence. And our own universe, in the distant, unimaginable future, may slow its expansion, reverse its course, and begin the long fall back toward another singularity, another bounce, giving birth to yet another cosmos. It is a grand and comforting vision, a universe that does not die but is eternally reborn, a great cosmic heart, beating once every few trillion years, a universe without a true beginning or end, only an endless cycle of breath, inhaling and exhaling worlds. There is another possibility, one born from the strange rules of the quantum world. Perhaps our universe is but one bubble in an infinite, bubbling foam of other universes, a multiverse. In this immense and staggering vision, new universes are constantly branching off, popping into existence from the quantum fluctuations of a greater apparent reality. Each bubble could have its own unique laws of physics, its own set of fundamental constants, its own history. Some might be sterile and empty. Others might be wildly different from our own, filled with forces and particles we cannot even imagine. We then would simply find ourselves in one of the bubbles where the conditions happen to be just right for stars, galaxies, and life to emerge. Our existence would not be a miracle of fine-tuning, but an inevitability of statistics. In an infinite garden of universes, a few are bound to have the right soil for life to grow. We are not the center of creation, but merely residents of one quiet, habitable corner of an infinitely vast and varied reality. We do not know which, if any, of these stories is true. They are the grand myths of our time, the poems we write to fill the silence at the dawn of time. And perhaps the question itself is the truest answer. The quiet, humble, and unending act of asking is what connects us to the great silent mystery from which we came. In the very first moments of creation, in the searing heat of the newborn universe, energy and matter were one and the same. Pure energy could spontaneously transform into pairs of particles, and these particles could instantly collide and vanish back into pure energy. For every particle of matter that flickered into existence, a perfect and equal twin was also born. An antiparticle. An electron would be born with its twin, a positron. A quark with an antiquark. These twins were identical in mass, but with an opposite electrical charge. They were perfect mirror images of each other, bound by a fatal symmetry. For when a particle and its antiparticle met, they would annihilate one another in a flash of pure light, leaving nothing behind but the energy from which they came. The early universe, then, was a place of perfect, furious, and ultimately futile balance. It was a cosmic storm of creation and destruction, a seething cauldron where for every birth there was an immediate and equal death. Imagine a dance of infinite partners. A particle is born, finds its perfect opposite partner, and they embrace in a final, brilliant burst of light. Another pair is born, and they too meet and vanish. For every step forward into existence, there was an equal and opposite step back into nothingness. If this perfect symmetry had held, if the dance had remained perfectly balanced, then as the universe expanded and cooled, every single particle would have found its antiparticle partner. They would have all annihilated each other. The cosmos today would be a cold, dark, and empty place, filled with nothing but a faint, diffuse sea of photons, the leftover light from that great final annihilation. There would be no matter, no galaxies, no stars, no planets, no life. The universe would be a beautiful, silent, and utterly sterile memorial to a perfectly balanced war where there were no survivors. And our existence, the fact that you are here to contemplate this, is proof that the symmetry was not perfect. The dance was not quite balanced. Somehow, for some reason we do not yet understand, the perfect symmetry was broken. In the chaos of the early universe, a tiny, almost imperceptible imbalance occurred. The laws of nature, it seems, had a slight preference for matter over antimatter. For every 1 billion pairs of antimatter particles that were created, there were 1,000,000,001 particles of matter. It was a cosmic rounding error, an imperfection on a scale so small it is almost impossible to grasp. But in that tiny flaw, in that single leftover particle for every billion annihilations, lay the seed of everything we know. As the universe cooled, the great annihilation proceeded. 1 billion particles of matter met their billion antimatter twins and vanished into light. But after the fire and the fury had subsided, after the last pairs had embraced and disappeared, a tiny residue was left behind, the lonely survivors. The 1 in 1 billion particles of matter with no one left to dance with. This is the substance of our world. Every star in the sky, every galaxy in the cosmos, every mountain, and every ocean, every living creature is made from the leftovers of that ancient, unequal war. We are the beautiful, improbable debris of a broken symmetry. Our solid, stable, and enduring reality is nothing more than a tiny, fortunate flaw in the otherwise perfect emptiness of what should have been. We live in a universe built on an exception to the rule. We are here because of a slight deviation in the grand cosmic plan, a subtle preference for something over nothing. The very fact of our being is a quiet testament to a profound and ancient imbalance. Our existence is not the norm, it is the anomaly. The vast, empty spaces between the stars are a silent reminder of the near-perfect annihilation that took place. And the stars themselves are the glowing embers of the matter that was saved from the fire. We often think of our universe as something grand and foundational, but in truth it is the faintest of echoes. It is the whisper that remained after the great shout of annihilation had faded. We are the survivors of a cosmic shipwreck, living on a tiny raft of matter in an ocean of leftover light. And in that realization lies a deep and humbling truth. Our world is not built on strength or certainty, but on a fragile, improbable, and beautiful imperfection. The question that haunts the heart of physics is simple and profound. Why? Why was the perfect symmetry between matter and antimatter broken? The standard theories of particle physics, the most successful scientific theories ever devised, predict that the balance should have been perfect. The laws of nature, as we currently understand them, show no significant preference for one over the other. The universe, according to our own rules, should be empty, and yet we are here. The very fact of our existence is the single greatest piece of evidence that our understanding of the universe is incomplete. There is some subtle, hidden law, some unknown force or particle that tipped the scales in that first, critical moment, ensuring that the cosmos would be filled with substance rather than an empty, silent light. Scientists around the world are searching for the source of this ancient imbalance. They are building vast, cathedral-like detectors to smash particles together at nearly the speed of light, recreating for a fleeting instant the fiery conditions of the early universe. In the debris of these collisions, they search for tiny, subtle differences in the way that matter and antimatter particles decay or interact. They are looking for the fingerprint of the force that chose us, the reason for our existence. The search is painstaking, like looking for a single, unique grain of sand on an infinite beach. They have found hints, subtle asymmetries in the behavior of certain exotic particles, but nothing yet that is powerful enough to explain the sheer scale of the matter that survived. The universe's preference for matter was far stronger than our current theories can account for. The mystery remains, as vast and as deep as the cosmos itself, and so we are left to wonder about the fate of that lost other universe. For every particle of matter that makes up our world, a corresponding particle of antimatter was annihilated. What if, somewhere, in some other corner of the cosmos, or in another universe entirely, the imbalance had gone the other way? Could there be entire galaxies, stars, and even life made of antimatter? A perfect mirror image of our own cosmos where positive is negative and left is right. From a distance, an antimatter star would look identical to a matter star. It would shine with the same light, be held together by the same gravity. But if a ship from our world were to ever meet a ship from theirs, the encounter would be the final, perfect annihilation. A burst of energy that would wipe both from existence, finally restoring the balance that was broken so long ago. Perhaps there is no such place. Perhaps the antimatter was simply the necessary sacrifice for our own creation. Its destiny was to disappear so that we could be. In this view, our universe is not just a survivor, but the sole beneficiary of a great cosmic injustice. We owe our existence to the disappearance of our twin. This is a humbling and strangely poignant thought, that the foundation of our reality is not a grand, positive act of creation, but a subtle act of subtraction. The universe did not so much create the world as it failed to completely destroy it. And in that beautiful failure, in that slight hesitation of the laws of nature, we find our home. The silence from the stars is not one of emptiness, but one of contemplation. It is the quiet, patient mystery of our own unlikely birth, a question written not in words, but in the simple, enduring, and improbable existence of the world around us. There are places in the cosmos where gravity, the gentlest of all forces, becomes a tyrant. These are the final collapsed cores of the most massive stars, objects so dense that they have torn a hole in the very fabric of reality. These are the black holes. They are not holes in the way we might think of a pit in the ground. They are not empty. They are, in fact, the most crowded places in the entire universe, containing the mass of several suns crushed into a point of infinite density. The gravity they exert is so powerful, so absolute, that nothing, not even light itself, can escape its grasp. They are the ultimate prisons of the cosmos, places from which no message can ever be sent, no cry can ever be heard. Surrounding this point of infinite density is an invisible, spherical boundary known as the event horizon. This is not a physical surface you could touch, it is a line of no return. Imagine it as the edge of a great waterfall in the river of space-time. Once you have drifted past this point, no amount of struggling, no amount of power can carry you back upstream. The current of space-time itself is flowing inward, toward the central singularity, faster than the speed of light. To escape would require traveling faster than light, a feat forbidden by the laws of the universe. And so, anything that crosses the event horizon, a wandering star, a cloud of gas, an unfortunate astronaut, is lost from our observable universe forever. Its light is extinguished, its story is silenced. It is pulled into the infinite silent point at the center, its substance adding to the black hole's mass, its identity erased from the cosmic record. We cannot see black holes directly, for they emit no light of their own. We see them only through their effects on the space around them. We see a star orbiting an empty point in space, whipping around an invisible massive partner in a frantic gravitational dance. We see a great swirling disk of gas and dust, called an accretion disk, spinning around the event horizon like water circling a drain. As this material is pulled inward, it is heated to millions of degrees by friction, glowing fiercely in X-rays and gamma rays just before it takes the final plunge. The black hole feeds on this material, its silhouette visible only because of the brilliant death cries of the matter it consumes. It is a darkness made visible only by the light it is about to destroy. This act of consumption, this final erasure of matter and energy from our universe, presents a quiet and profound problem. The information that is contained within an object, its structure, its composition, its history seems to be utterly and permanently lost when it falls into a black hole. Imagine throwing a book into a fire. The book is destroyed, but in principle, if you could track every single particle of smoke and ash, every photon of light and heat, you could reconstruct the information that was in the book. The story would still exist, scattered and disordered, but not truly gone. But a black hole seems different. It takes the book, with its intricate story, and reduces it to just 3 simple properties: mass, spin, and charge. The story itself, the information, seems to vanish without a trace. It is as if the universe's memory has been selectively erased. The book not just burned, but completely and utterly forgotten. This idea that information can be permanently destroyed strikes at the very heart of physics. One of the most fundamental and deeply held principles of the quantum world is that information is always conserved. It can be scrambled, hidden, or rearranged, but it can never be truly lost. The universe, at its most basic level, is believed to be a perfect record keeper. The total amount of information in a closed system must always remain the same. This principle is as central to quantum mechanics as the conservation of energy is to classical physics. If a black hole can truly destroy information, then our understanding of quantum mechanics, one of the twin pillars upon which all of modern physics rests, is fundamentally flawed. The universe is not a perfect record keeper. It is forgetful. And this is the black hole information paradox. The conflict is a quiet, but monumental one, a deep and unsettling schism between the 2 great theories that describe our cosmos. On one side stands Einstein's theory of general relativity, the theory of gravity, which describes black holes as simple information, destroying objects with smooth, featureless event horizons. On the other side stands quantum mechanics, the theory of the very small, which insists that information must be preserved, no matter what. For decades, these 2 pillars of our understanding have stood in silent contradiction. A black hole cannot be both a perfect information destroyer and a perfect information preserver. One of them, or perhaps both, must be incomplete. The event horizon of a black hole is the place where our 2 greatest stories about the universe collide, the quiet, dark battleground where our deepest understanding of reality breaks down. The great physicist Stephen Hawking offered a potential and equally strange resolution. He discovered that black holes are not entirely black. Due to subtle quantum effects at the event horizon, they should glow with a faint, cold radiation, now known as Hawking radiation. Over immense, almost unimaginable periods of time, a black hole will slowly lose mass through this radiation, growing smaller and smaller until it eventually evaporates completely, disappearing in a final, quiet puff of energy. This discovery seemed to make the paradox even worse. If the black hole evaporates, then the information that fell into it is not just locked away, but is truly gone from the universe forever. But it also offered a glimmer of hope. Perhaps somehow the information is not destroyed. Perhaps it is subtly encoded in the faint, outgoing Hawking radiation. Imagine the information from the book being scrambled and imprinted in some incredibly complex way onto the individual particles of light and heat that are emitted as the black hole evaporates. The story would not be lost, but would be returned to the universe in a new, almost unrecognizably scrambled form. To reconstruct the book would require collecting every single particle of Hawking radiation over trillions of years and performing an impossibly complex calculation. But in principle, the story would still be there. The universe's memory would be preserved. This idea that the event horizon is not a smooth, featureless abyss, but a roiling quantum firewall that imprints information onto outgoing radiation, is one of the leading contenders for solving the paradox. But it comes at a cost. It would mean that the smooth, gentle space-time described by Einstein's theory is not the whole story. At the edge of a black hole, the fabric of reality itself would be a chaotic, fiery, and quantum mechanical storm. An astronaut falling in would not drift peacefully across the horizon, but would be instantly incinerated by a wall of high-energy particles. We do not yet know the answer. The paradox remains one of the greatest unsolved mysteries in physics, a quiet, stubborn knot in our understanding of the cosmos. It is a reminder that the universe, in its most extreme corners, still holds secrets that challenge our deepest intuitions. A black hole is more than just a dead star. It is a philosophical object. It is the place where time and space come to an end, and where the two great pillars of our knowledge are forced to confront one another. The silent, dark surface of the event horizon is the ultimate frontier, not just of space, but of thought itself. And in its quiet, patient existence, it asks us a simple, profound question. What is the true nature of reality? And what happens to a story when it falls into a place where all stories end? As we gaze out into the cosmos, we see a universe that appears to be exquisitely tuned for life. The fundamental constants of nature, the unchanging numbers that underpin all of the laws of physics, seem to have values that fall within an extraordinarily narrow range that allows for the existence of complexity. If any of these constants were even slightly different, the universe as we know it would be impossible. The stars would not shine. Galaxies would not form. The intricate chemistry of life could never have begun. Our existence seems to depend on a series of cosmic coincidences so improbable, so precise, that it is difficult to accept them as mere chance. It is as if we are living in a universe that was built just for us. Consider the strength of gravity. It is by far the weakest of the four fundamental forces, but its value is perfectly balanced. If gravity were just a tiny fraction stronger, stars would burn through their fuel much more quickly and violently. They would be more massive, hotter, and would live for only a few million years. Not nearly long enough for the slow, patient process of evolution to give rise to complex life on any orbiting planets. If gravity were slightly weaker, the initial clumps of matter in the early universe would never have been able to coalesce into the first stars and galaxies. The cosmos would have remained a thin, cold, and eternally diffuse soup of hydrogen and helium, a universe without structure, without fire, without homes for life. Our universe exists on a knife's edge, in the delicate balance between a cosmos that burns out too quickly and one that never ignites at all. Or consider the force that binds atomic nuclei together, the strong nuclear force. Its strength is what allows protons and neutrons to cling to each other, forming the stable elements that are the building blocks of our world. If this force were just 2% weaker, protons would not be able to stick together, and the only element in the universe would be hydrogen. There would be no carbon, the backbone of all known life, no oxygen to breathe, no iron to carry that oxygen through our veins. If the strong force were just 0.5% stronger, all of the hydrogen in the early universe would have been fused into heavier elements in the first few minutes after the Big Bang. There would be no hydrogen left to fuel the long-lived, stable stars like our sun. There would be no water. The intricate dance of chemistry that makes life possible depends on this force being exactly as strong as it is, no more and no less. The list of these apparent coincidences goes on and on. The mass of the neutron is slightly heavier than the mass of the proton, a tiny difference that allows for the stability of atoms. If it were the other way around, all protons would have decayed into neutrons, and atoms could not exist. The amount of dark energy that is causing the universe to accelerate is astoundingly small. If it were larger, its repulsive force would have torn the universe apart before galaxies could even form. If it were zero, the universe might have collapsed back on itself long ago. The universe seems to be balanced on a razor's edge, a symphony of fundamental constants all playing in perfect, improbable harmony. It is a harmony that allows for the existence of structure, for the formation of stars, for the slow, beautiful unfolding of chemistry, biology, and consciousness. The very fact that we are here to observe the universe, to wonder about its nature, seems to be a consequence of this extraordinary and delicate fine-tuning, this apparent design, this Goldilocks universe where everything is just right, presents us with a deep and unsettling philosophical question. How do we explain this incredible string of cosmic luck? There are three main paths our minds can wander down, each as profound and as unprovable as the next. The first, and perhaps the most ancient, is the idea of a creator. The fine-tuning of the universe, in this view, is not a coincidence at all, but the deliberate act of a cosmic designer, a divine intelligence that set the dials of the universe's laws to the precise values needed for life to emerge. Our universe is not an accident, but a purposeful creation. It is a thought that has brought comfort and meaning to humanity for millennia. The idea that our existence is not a random outcome, but part of a grand intentional story. Science cannot prove or disprove this idea. It lies outside the realm of testable hypotheses, in the quiet, personal space of faith. The second path is to accept that we are simply the beneficiaries of an extraordinarily improbable, but not impossible, stroke of luck. There's only one universe, and we just happen to live in it. The fundamental constants have the values they have for no particular reason, and it is simply a brute fact of our existence that they allow for life. This idea is scientifically consistent, but for many, it feels deeply unsatisfying. It leaves the astonishing precision of the universe as a complete and utter mystery. It asks us to accept that we won the cosmic lottery, a lottery with odds so astronomically high that they are functionally indistinguishable from zero. It is a universe of pure, unadulterated chance, where our existence is the most unlikely and beautiful accident in the history of time. The third path leads us back to the strange and wonderful idea of the multiverse. Perhaps our universe is not the only one. Perhaps it is just one bubble in an infinite foam of other universes, each with its own randomly assigned set of physical laws and fundamental constants. In this vast cosmic landscape of possibilities, almost all of these other universes would be sterile and dead. Some would collapse in an instant. Others would be empty voids of thin gas. Some might have forces so strong that no structures could form. But in an infinite collection of universes, it is inevitable that a few, by pure chance, would happen to have the right combination of laws and constants for life to emerge. And of course, we would find ourselves living in one of those rare, hospitable universes, because we could not exist anywhere else. Our existence is not a miracle. It is a selection effect. We are here to observe our universe as fine, tuning for the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere, We could not have evolved anywhere else. This idea, the anthropic principle, removes the need for a designer or for incredible luck. Our finely tuned universe is not special. It is simply the one we are capable of inhabiting. We do not know which of these paths is the correct one. They are all grand, sweeping narratives that we create to make sense of our own improbable existence. They are the stories we tell ourselves in the face of a cosmos that seems both impossibly random and exquisitely ordered. The fine-tuning of the universe does not provide us with an answer. It provides us with a profound and lasting sense of wonder. It is a quiet, persistent whisper from the cosmos, a reminder that the world is a far more mysterious and delicate place than we might ever have imagined. And in the face of that mystery, we are left with a simple, humbling gratitude for the sheer, improbable fact of our own being. A fleeting moment of consciousness in a universe that seems to have been perfectly, beautifully, and inexplicably made for us. We move through the world as if it were a stage, a solid, dependable platform upon which the drama of our lives unfolds. We experience space as the empty distance between objects, and time as the steady, inexorable river that carries us from the past into the future. They feel separate, absolute, and unchanging. A meter is always a meter. A second is always a second. This is the intuitive reality of our daily lives. The world is described by Isaac Newton, a universe of fixed grids and universal clocks. It is a simple and comforting picture, a cosmos that is stable, predictable, and independent of our own motion or presence. It is a universe where space is the container, and we are merely the contents. But 100 years ago, a revolutionary idea reshaped our understanding of this fundamental stage. Albert Einstein, in his theory of general relativity, revealed that space and time are not separate entities, nor are they a passive backdrop. They are interwoven into a single, dynamic, four-dimensional fabric, space-time. This fabric is not rigid. It is soft, flexible, and alive. It can be bent, stretched, and warped by the presence of matter and energy. Imagine a vast, taut sheet of rubber. A bowling ball placed in its center will create a deep dimple, a curvature in the sheet. A marble rolled nearby will not travel in a straight line, but will be guided by this curvature, spiraling inward toward the bowling ball. This, Einstein proposed, is what we perceive as gravity. Gravity is not a mysterious force that acts across a distance. It is the shape of space-time itself. The Earth is not being pulled by the Sunday. It is following the straightest possible path through the curved space-time created by the Sunday's immense mass. This is a universe of profound and beautiful elegance. The motion of the planets, the arc of a thrown stone, the spiraling dance of distant galaxies are all governed by this simple, underlying principle. Matter tells space-time how to curve, and curved space-time tells matter how to move. The universe is no longer a static stage, but a dynamic, interactive system, a great cosmic dance between matter and the geometry of reality itself. Your own body right now is creating a tiny, imperceptible warp in the space-time around you. The entire planet is falling through the gentle, sloping valley in space-time created by our sun, and our sun is orbiting the great, deep gravitational well at the center of the Milky Way galaxy. We are all travelers on the gentle, invisible currents of a four-dimensional ocean, our paths dictated not by forces, but by the very shape of the water. This fabric of space-time can also ripple, just as a stone dropped into a pond creates waves that travel outward. A massive accelerating object in the cosmos will create ripples in the fabric of space-time. These are gravitational waves. They are tremors in the geometry of reality, stretching and squeezing space as they pass by. The most violent events in the universe, the collision of two black holes, the merger of two neutron stars, send these waves propagating across the cosmos at the speed of light. For billions of years they travel in silence, their passage almost imperceptible. As a gravitational wave passes through you, it stretches your body in one direction and squeezes it in another, by an amount smaller than the width of a single atomic nucleus. We have only recently, with instruments of almost unimaginable sensitivity, been able to detect these faint ancient whispers from the cosmos. When we feel them, we are not seeing light from a distant event. We are feeling the very reverberation of space-time itself, the echo of a cosmic cataclysm that happened 1 billion years ago, finally washing over our quiet shore. This is the universe as a smooth, continuous, and dynamic whole, a graceful, flowing entity where the stage and the actors are one and the same. The image of space-time as a smooth, continuous sheet of rubber is a powerful one. It has guided our understanding of the cosmos for a century, and it works perfectly on the grand scales of planets, stars, and galaxies. But in the strange and counterintuitive world of quantum mechanics, the world of the very small, the idea of perfect smoothness begins to break down. Quantum theory tells us that energy is not continuous, but comes in discrete, indivisible packets, or quanta. A beam of light is not a smooth wave, but a stream of individual photons. In the quantum realm, reality is not a gentle slope, but a grainy, pixelated staircase. And so, a profound question arises: what about space-time itself? If we could zoom in far beyond the scale of atoms and nuclei to the smallest possible distances imaginable, would we still see a smooth, continuous fabric? Or would we find that space-time, too, is made of tiny, indivisible pixels? This is one of the deepest and most challenging frontiers in all of physics, the quest for a theory of quantum gravity. It is the attempt to reconcile the two great pillars of our knowledge, the smooth, geometric world of Einstein's relativity and the grainy, probabilistic world of quantum mechanics. At the moment, these two theories speak different languages. Relativity describes a universe that is deterministic and continuous, while quantum mechanics describes a universe that is fuzzy, uncertain, and quantized. To understand the origin of the universe in the Big Bang, or the true nature of a black hole's singularity, we need a single unified theory that can describe how gravity behaves in the quantum realm. We need to know what space-time is made of. The scale at which these quantum effects of gravity are thought to become important is known as the Planck length. It is a distance so unimaginably small that it defies all of our everyday intuition. If you were to scale up a single atom to be the size of the entire observable universe, the Planck length would be about the height of a single tree. At this fundamental granular level, the very notions of space and distance may lose their meaning. Space-time may cease to be a smooth fabric and instead become a roiling, chaotic foam of quantum fluctuations, a turbulent sea where tiny wormhole-like structures and miniature universes pop in and out of existence in a fleeting, timeless dance. Our smooth, stable, and predictable reality would be nothing more than the calm, averaged out behavior of this incredibly violent and chaotic substructure, just as the smooth surface of the ocean belies the frantic motion of its individual water molecules. This idea that space-time is not fundamental but is an emergent property of some deeper quantum reality is a profound shift in our perspective. It suggests that the stage of the universe is not what it seems. Space and time, the most basic and fundamental aspects of our experience, may not be the primary ingredients of reality, but rather a collective illusion, a pattern that emerges from the interactions of more fundamental information, like bits that do not exist in space or time at all. It is as if the universe, at its deepest level, is not a physical object, but a vast quantum computer, and the three-dimensional space we perceive is its holographic projection. The story of the cosmos, in this view, is not written on space-time, but is encoded in a network of quantum information. And space-time itself is just the way we read the story. We are still far from a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches are all beautiful, intricate mathematical frameworks that attempt to describe this fundamental, pixelated nature of reality. But we do not yet know which, if any of them, is correct. The energies required to probe the Planck scale directly are so vast that they are far beyond the reach of any conceivable particle accelerator. And so, we are left to search for clues in the faint, ancient light from the early universe, or in the subtle whispers of gravitational waves, hoping to find a tiny telltale sign of the grainy nature of space-time. For now, the question remains: is reality a smooth and flowing river, as Einstein imagined, or is it a digital image constructed from an infinite number of tiny, indivisible pixels? The answer lies hidden at the very bottom of space, at the beginning of time, in a realm of quiet quantum chaos that holds the secret to the true nature of the stage on which we live. There is a connection in the quantum world that Albert Einstein famously called spooky action at a distance. It is a phenomenon so strange, so counterintuitive, that it seems to violate our most deeply held beliefs about the nature of reality. It is called quantum entanglement, and it suggests a hidden layer of connectedness in the universe, a subtle, invisible web that ties the fates of particles together, no matter how far apart they may be. Imagine you have a pair of particles, perhaps two photons, that are created together in such a way that their properties are linked. For example, they might be created with opposite spins. If one is spinning clockwise, the other must be spinning counterclockwise. In the quantum world, before you measure it, a particle's spin is not fixed. It exists in a fuzzy probabilistic state of all possibilities at once. It is both clockwise and counterclockwise simultaneously. Now, let's separate these two entangled particles. We send one to the other side of the room and the other to the far side of the galaxy. They are now separated by billions of light years. According to our classical intuition, they are now two independent objects, their connection broken by the vast, empty distance between them. But in the quantum world, this is not the case. The moment you measure the spin of the particle on this side of the galaxy, and let's say you find it is spinning clockwise, you instantly know with absolute certainty that the other particle, billions of light years away is spinning counterclockwise. The spooky part is not just that you know it. The act of measuring the first particle seems to have instantly forced the second particle to choose the opposite spin. It collapses from its fuzzy state of all possibilities into a single definite reality, and it does so at the exact same moment as its distant twin. This connection appears to be instantaneous. It does not travel through space at the speed of light. It seems to happen outside of time, in a way that defies our understanding of cause and effect. How does the second particle know what happened to the first? How is this information transmitted across billions of light years in no time at all? Einstein believed that this apparent faster, than light communication meant that quantum mechanics was incomplete. There must be some hidden information, some hidden variables, that the particles carried with them from the moment of their creation, like a set of secret, pre-written instructions. In this view, there is no spooky action. The particles were always predestined to have opposite spins. We just didn't know it until we measured one of them. It would be like putting one red marble and one blue marble into two separate identical boxes, shuffling them and sending them to opposite ends of the universe. When you open your box and find a red marble, you instantly know the other box contains a blue one. There is no mystery, no spooky connection. The information was always there. For decades, this was a philosophical debate. But in the 1960s, a physicist named John Bell devised a brilliant mathematical test that could distinguish between Einstein's hidden variables and the spooky interconnectedness of quantum mechanics. Experiments have now been carried out many times with exquisite precision, and the result is unambiguous. Einstein was wrong. There are no hidden variables. The spookiness is real. The universe is, at its deepest level, non-local. The fates of entangled particles are not predetermined. They are linked by a mysterious, holistic connection that transcends our normal notions of space and separation. The act of observing a particle here and now can have an instantaneous effect on a particle on the far side of the cosmos. This does not mean we can use entanglement to send faster than light messages. The outcome of any individual measurement is still random. You cannot force your particle to be clockwise or counterclockwise, and so you cannot use it to send a predetermined signal. The connection is a correlation, not a communication channel. But it is a correlation that fundamentally changes our picture of reality. It suggests that the universe is not a collection of separate, independent objects, but a single, indivisible whole. The idea of distance and separation may be an illusion of our macroscopic perspective. At the fundamental, quantum level, there may be no such thing as here and there. Everything is, in some deep and mysterious way, connected to everything else. What is the nature of this connection? We do not know. It is not a force that travels through space. It is not an energy that can be measured. It seems to be a fundamental property of reality itself, a whisper of a deeper, more interconnected order that lies beneath the surface of our everyday world. It is as if the fabric of space-time, which we perceive as separating things, is woven from a more fundamental set of threads of quantum entanglement that link every point in the universe together. The space between two entangled particles is not an empty void, but a bridge, an invisible, timeless umbilical cord that maintains their connection. This idea leads to some staggering and beautiful possibilities. It could be that the very structure of space-time itself is an emergent property of this vast cosmic web of entanglement. The geometry of our universe, the feeling of distance, the force of gravity, might all be macroscopic manifestations of the intricate pattern of quantum connections between the fundamental bits of information that make up reality. In this view, the universe is not a container filled with things, but a single, vast quantum computational network. The spooky action at a distance is not a violation of locality, but a glimpse of the true, underlying architecture of reality, a reality where the concept of locality does not apply. We are not just living in the universe, we are a part of its intricate, interconnected web. Every particle in your body may be subtly, anciently entangled with particles in a distant star or a far-flung galaxy. We are all, in the most profound and literal sense, connected. And in that quiet, spooky, and beautiful truth, the loneliness of the vast, dark cosmos begins to fade away. When we look out into the deepest reaches of the cosmos, in any direction we choose, we see a universe of remarkable uniformity. We are seeing the oldest light in existence, the faint afterglow of the Big Bang, which was released when the universe was just a few 100,000 years old. This light, known as the cosmic microwave background, bathes the entire sky in a faint, cold, and almost perfectly even glow. Its temperature is the same everywhere we look, to an astonishing precision of 1 part in 100,000. It is as if the entire observable universe, when it was still in its infancy, had somehow reached a perfect state of thermal equilibrium. Every region of the cosmos had the exact same temperature. This uniformity is a profound and beautiful puzzle. Imagine 2 cups of coffee, one on your table and one on the moon. If you were to measure their temperatures and find them to be identical, down to the tiniest fraction of a degree, you would naturally assume they had been in contact at some point, or had been brewed from the same pot. Heat can only be exchanged, and temperatures can only be equalized, if there is a way for information and energy to travel between 2 points. In the early universe, the ultimate speed limit for any such exchange was the speed of light. And this is where the mystery, known as the horizon problem, begins. Let us look at 2 opposite points in the sky. The ancient light from one of these points has been traveling for nearly 14 billion years to reach us. The light from the opposite point has also been traveling for 14 billion years. This means that, at the time this light was first released, these 2 regions of the early universe were separated by a distance of nearly 28 billion light years. But the universe at that time was only 380,000 years old. There simply had not been enough time for a light signal or any other causal influence to have traveled from one of these regions to the other. They were causally disconnected. They were outside of each other's horizon. They had never been in contact. They had never had the chance to exchange heat or information. They should not have known about each other's existence. And yet, they have the same temperature. It is as if 2 people who had never met, never spoken, and lived on opposite sides of the world, independently decided to paint their houses the exact same shade of blue, down to the molecular level. It is a coincidence on a cosmic scale. A uniformity so profound and so seemingly impossible that it demands an explanation. How did these distant, disconnected regions of the early universe all agree on the same temperature? What quiet, unseen mechanism was at work, coordinating the entire cosmos in its first moments, ensuring that it would be born with this incredible smoothness and balance. The universe, it seems, was born with a shared memory of a state it should never have been able to create. The leading and most widely accepted explanation for this astonishing uniformity is a theory known as cosmic inflation. This idea proposes that in the very first, fleeting fraction of a second after the Big Bang, the universe underwent a period of accelerated exponential expansion. In a time frame shorter than the blink of an eye, a region of space smaller than a proton was stretched to a size larger than the entire observable universe today. It was an expansion of space itself, a stretching of the cosmic fabric so violent and so rapid that it dwarfs any other process in the history of the cosmos. This period of inflation provides a beautiful and elegant solution to the horizon problem. Before inflation began, the entire region that would eventually become our observable universe was an incredibly tiny subatomic patch of space. It was so small that it was causally connected. There was plenty of time for this tiny patch to reach a state of perfect thermal equilibrium, for every point within it to share the same temperature and properties. Then inflation happened. This tiny, smooth, and uniform patch was suddenly and violently stretched to a colossal size. The uniformity was locked in, stretched across the entire cosmos. The reason that distant, opposite sides of our sky have the same temperature today is because, long ago, before the Great Expansion, they were once neighbors. They were once part of the same tiny equilibrated region. They are not strangers who miraculously share the same properties. They are long-lost twins, separated at birth by the most incredible expansion in the history of time. Inflation also explains the flatness of our universe and the origin of the tiny temperature fluctuations that would eventually grow into the great clusters of galaxies. It is a powerful and all-encompassing theory, a single elegant idea that solves many of the deepest puzzles of cosmology at once. It paints a picture of our universe as the product of a runaway quantum process in the first moment of time, a universe born not from a gentle unfolding, but from a brief and unimaginably violent stretching of reality itself. We are living in the quiet, peaceful aftermath of this ancient cosmic storm. But the theory of inflation, for all its beauty and power, remains a theory. We do not yet have direct, conclusive proof that it happened. We do not know what caused it, what the inflated field that drove it was, or why it suddenly stopped. And it leads to its own set of profound and mind-bending consequences, such as the possibility that our universe is just one of an infinite number of bubble universes, each born from its own inflationary event in a greater, eternal multiverse. The quiet, uniform glow of the night sky, which appears so serene and so peaceful, may be the echo of the most violent and extreme event in the history of everything. It is a quiet cosmic hum that speaks of a time when the universe was smaller than an atom and expanded faster than the speed of light. It is a beautiful, silent testament to a past so strange and so extreme that it borders on the edge of what we can imagine. And it is a reminder that the most peaceful and stable things we see in the cosmos are often born from the most chaotic and unimaginable beginnings. The galaxy is a vast and ancient city of stars, a swirling metropolis containing hundreds of billions of suns. And around many of those suns, we now know there are planets. Our own solar system is not a unique miracle, but a common and natural outcome of star formation. Based on what we have learned in just the last few decades, It is estimated that there may be tens of billions of Earth, like planets in the Milky Way alone, worlds orbiting in the gentle Goldilocks zone of their stars, where liquid water, the solvent of life as we know it, could exist. The raw ingredients for life, carbon, oxygen, water, are abundant throughout the cosmos, forged in the hearts of stars and scattered through interstellar space. The universe, it seems, is a fertile place filled with countless potential cradles for biology, and our universe is old. Life on Earth emerged relatively quickly after our planet formed, and it has had billions of years to evolve into the complex, intelligent species that is now capable of looking out into the cosmos and wondering if it is alone. But our sun is a relatively young star. There are billions of other stars in our galaxy that are far older, some by billions of years. If life is a common occurrence, then it is almost certain that it would have arisen on some of these older, Earth-like planets long ago. There should have been countless opportunities for other civilizations to emerge, to develop technology, and to begin exploring the stars. Some of them could have had a head start of millions or even billions of years on us. A civilization with such a head start would have had more than enough time to develop technologies far beyond our own, including the ability to travel between the stars, or at the very least, to send out powerful, unmistakable signals of their existence. The galaxy should be teeming with their probes, their artifacts, their radio messages. The night sky should be alive with the signs of their presence, and yet we see nothing. We hear nothing. When we point our most sensitive radio telescopes at the stars, we are met only with the quiet cosmic hiss of empty space. When we scan the sky for the strange artificial light of alien technologies, we find only the natural, steady glow of suns. The galaxy, for all of its apparent potential, appears to be silent, empty, and uninhabited. This is the Fermi paradox. The universe tells us that intelligent life should be common, but the evidence tells us that it is nowhere to be found. The great cosmic city of stars appears to be a ghost town, and so we are left with the profound and unsettling question that the physicist Enrico Fermi first asked over a casual lunch in 1950. Where is everybody? This silent, empty sky has haunted our thoughts for decades, and it has given rise to a host of possible and often chilling explanations. Perhaps the simplest and most lonely explanation is that we are, in fact, alone. The emergence of life, or perhaps the leap from simple life to complex, intelligent life, may be an event of such staggering improbability that it has happened only once in the entire history of our galaxy. The long chain of fortunate accidents that led to our existence. The stable star, the right-sized planet, the large moon, the exact chemical composition, the long periods of climatic stability, may be so rare that we are the sole beneficiaries. We are not just one civilization among many, but the only consciousness the galaxy has ever known. It is a thought of profound and almost unbearable solitude, that in all this vast, magnificent darkness we are the only ones to have ever woken up. Or perhaps civilizations do arise, but they do not last. This is the idea of the Great Filter. It suggests that there is some inevitable and powerful barrier that prevents intelligent life from reaching a star-faring stage. This filter could be in our past, Perhaps the leap from non-life to life, or from single-celled organisms to complex animals, is the incredibly difficult step that almost no one passes. If this is the case, we are among the lucky few who have made it through. But the filter could also be in our future. Perhaps all advanced civilizations, upon reaching a certain level of technological prowess, inevitably destroy themselves through nuclear war, environmental collapse, or some other unforeseen catastrophe. In this sobering view, the silence of the cosmos is not a sign of emptiness, but a warning. The quiet from the stars is the sound of other civilizations having failed the final test, and we are now approaching that same test ourselves. There is another, less bleak, set of possibilities. Perhaps the galaxy is teeming with life, but we are simply unable to see it or hear it. Perhaps they are not using radio waves, but some other more advanced form of communication, like neutrinos or gravitational waves, that we do not yet know how to listen for. It would be like searching for text messages with an FM radio. Perhaps they are out there, but they are deliberately hiding from us, following some sort of galactic code of non-interference, treating our young, noisy planet like a wildlife preserve to be observed from a distance, but never contacted. Or perhaps, the most mind-bending possibility of all, they are here, all around us, in forms so advanced and so alien that we do not even recognize them as life. Their consciousness may exist in the quantum fluctuations of the vacuum, or in the complex magnetic fields of a nebula. We are like ants on an anthill next to a 10-lane superhighway, completely oblivious to the vast, complex, and intelligent traffic that is passing by us every single moment. The universe is not silent. We are simply deaf. We do not know which of these stories is true. The Fermi paradox is not a contradiction in our physics, but a contradiction in our expectations. It is the vast, echoing space between the promise of a living universe and the reality of a silent one, and it forces us to confront our own place in the cosmos in the most profound way possible. Are we the first, the last, or simply the most isolated? The quiet of the night sky is not an empty canvas. It is a question mark. It is a mirror reflecting our own hopes, our own fears, and our own profound and beautiful loneliness. The silence from the stars is not an answer. It is an invitation to listen more closely. And now, the stars begin to dim behind your thoughts. We have drifted through 100 years of quiet questions, from the invisible scaffolding of the galaxy to the silent, empty sky. We have not found answers. We have simply floated for a while in the vast, gentle sea of what is not yet known. These mysteries are not meant to trouble you. They are the universe's lullabies. They are the deep, soft background against which the stars shine so brightly. You are a part of this mystery. The atoms in your body follow the same strange quantum rules, bend the same smooth space-time, and are made from the same stardust that survived the great ancient imbalance. The questions of the cosmos are not outside of you. They are woven into the very fabric of your being. Tonight, as you rest, the universe continues its slow, silent, and magnificent unfolding, and you are floating within it, a small, warm, and precious consciousness resting in the quiet heart of a great and beautiful mystery. Let these grand questions dissolve now. Let them become distant, gentle stars in the soft darkness of your mind. There is nothing left to solve, nothing left to understand. There is only the quiet, steady rhythm of your own breath, a gentle tide pulling you out into the deep, peaceful, and silent ocean of sleep. Sleep well and dream softly. Good night.